Alright, hey guys, what is going on? Today we are going to get our feet wet with twistors now. Twistors are a very interesting, unique mathematical object that Roger Penrose postulated back in the 1960s. And ever since then, it's become a very interesting area of physics. Right? And so what we're going to do here is we're going to just briefly introduce ourselves to what is called the incidence relation. And the incidence relation is at the core of twistor theory. Okay, we want to keep in mind also that the attempt here is to unify quantum physics with general relativity. And when we do that, we get a bunch of infinities that we can't deal with. There's a lot of problems, okay? And Roger Penrose, his theory was we need to think about not quantizing gravity. In fact, his famous quote from one of his videos on YouTube, maybe it's not famous, but it's a quote of his, is that we should forget about quantizing gravity. Rather, what Roger Penrose postulated was that instead of quantizing gravity, we should complexify spacetime. And when we complexify spacetime, what happens is that we get a higher dimensional space, if you will. And space-time, as we live in it, as we know it, is just a subset of this higher dimensional thing. And objects in that higher dimensional space are twistors. So let's go ahead and start getting our feet wet with this stuff. So in this video, I have one animation that I want to sort of get to you guys, and so that you can begin to understand sort of the geometry of twistors here. And that animation is seen right here. And in this animation, you might not be seeing much, but we have these dials that are going to indicate positions, if you will, not position, but parameterizations of spacetime, right? So if you move in space, the bars on the far left, the three bars on the far left, are going to be moving. That's going to correlate to if you move in X, Y, and Z directions. And then if you don't move in space and you're just moving in time, that's going to correspond to that rightermost bar. Okay, and then as we can change values of these space-time events, and as we do that, we are modulating a vector on the far right, my right, of this animation. And we'll break this down in some more depth as we go through the video. So the first steps that we took in the past few videos is we said we were interested in vectors and turning them into Pauli vectors and Weyl vectors. Again, Pauli vectors and Weyl vectors were just vectors, but sandwiched between two Pauli matrices, or two unitary matrices. Okay, and when we did that, we got these sort of newly casted vectors, and these newly casted vectors is what we called the Pauli and the Weyl vectors. We were then able to take these vectors, these Pauli and Weyl vectors, specifically Weyl vectors. We're looking specifically at Weyl vectors. Those are the vectors that were, those were the ones that incorporated time into them. And what ended up happening is that we were able to break those down into two component objects, and those were spinors, or Weyl spinors. These Weyl spinors were the outer product, or the outer product of these spinors were the Weyl vectors themselves, right? So the idea here again is that you have these two Weyl spinors, take their outer product together, and you get something like a Weyl vector. And a Weyl vector is just a vector sandwiched in between two unitary orthogonal two unitary matrices. These are the Pauli matrices. All right, I'm going to be repeating myself quite a bit here because I think it's good to constantly repeat ourselves as we go through advanced physics so we don't lose sight of what we're actually doing. When we look at our Weyl vector, we see that there is an A and an A prime in the superscript of our spacetime, right? So if the spacetime is X, right, that's going to also incorporate time. But the A and the A prime refer to the spinors, right? So you have A, which is the first spinor, and then A prime is the complex conjugated version or correlate to that spinor. And much like a dual vector, when applied to a vector in general relativity, gives us a number. You can, if you've taken general relativity, you should be very familiar with that concept. the idea here is that a spinor applied to its complex conjugated spinor is going to give us a vial vector. Okay. And so this is how this is going to be constructed. We have these, again, these vial spinors, and we have these vial vectors, which are all sort of just newly casted versions of a space-time vector. So as we proceed with twistor theory, we want to organize things in our mind. So as I was talking about, we had spinors. Now those exist in a spinor space, okay? These are two-dimensional objects. It's a two-dimensional space. They're the simplest objects that we can think of. They are what make up the vial vectors. They live in this spinor space. It's a two-dimensional space, okay? But then we also have their complex conjugated spinors. Those complex conjugated spinors live in their own space as well. Those complex conjugated spinors are going to have a prime on them, and this is what you see in the literature. And we were able to create dual spinors, and dual spinors were, again, if we applied the spinor metric, we talked about the spinor metric to our spinor, we get a dual spinor. Okay, and we talked about this in previous videos as well, when we had a big table showing up, and that table showed us everything on how left chiral spinors and right chiral spinors were related to each other, and how all of that was sort of related to each other. I'll show that again here. But the idea here, again, is that we really just want to organize the primes and the stars and everything in our minds so that we can go forward in understanding this sort of all the nomenclature behind this physics. And if you're familiar with tensor calculus, the next logical step that we can take here is to take tensor products of these spaces. Okay, and so what we get are things that are higher in valence. In the tensor language, these are usually called higher rank tensors. In the spinor language, these are usually called higher valence spinors. Okay, and these spinors these higher valence spinors are very, very important here. As you can see here, or down here actually, when we talk about fields and particles within these fields, or particles that are made of these fields, what these higher valence spinors are going to represent are things that have a more interesting internal degrees of symmetry. These higher valence spinors are also going to be very useful in helping us understand particles with higher spins, or they're also going to be able to help us understand combinations of particles as well. So these higher valence spinors are going to be very, very useful later on when we start talking about more multi-particle physics. But what we want to do now is get into some of the nitty-gritty mathematics, and I'm going to go to my whiteboard for that. Alright, so we're at the whiteboard now. We're going to be talking about spinors and the incidence relationship, and we're going to get kind of deep into this so that we can really understand it. And then we're going to go to some code to illustrate the animation that I was talking about earlier. So let's go ahead and get started. So in the last few videos, we talked about how vial vectors could be used or could be decomposed into their vial spinors, and the spinors again were two component objects, right? So, and the components of both of those spinors were related to each other in that one was one was the complex conjugate of the other one, and so then we were able to relate the two. We were able to relate the components of the spinors to the components of the vectors, and in doing that, we got this relationship right here, or these relationships right here, right? So these guys right here. And it's important to keep in mind now that we're not talking about a vector like an electromagnetic field vector or something like that. We're talking about a space-time vector. This is a space-time point, right? So you exist at some point in X, you exist at some point in Y, some point in Z or Z, however you say it. But you also exist in time as well, right? So these are our space-time components, right? That's these guys right here, right? And so these are the space-time components. Space-time components, right? And so from this then, these were the relationships that we got last time, okay? And then we also got this relationship here, and so this is space-time deconstructed into its spinor components. When we include time, this is the vial vector decomposed into vial spinors. And everything in terms of those components. And so the spinors, these are the vial spinors right here. These are the vial spinors. Vial spinors. Ooh. Spinors. This is the vial vector. Kind of say it's similar to a polyvector, but it's not exactly a polyvector. And the reason for that, again, is because we have this component of time. All right, so moving on. Now the central idea here that Roger Penrose postulated is that, okay, we want to take this spacetime, right? So spacetime is this thing right here, spacetime point. Spacetime point. And we're going to take that spacetime point and we're going to say that that point is, excuse me, going to be complexified. And when we complexify that point, what we're going to do, we're not merely just going to say, we're not merely just going to do this where we have like C, T, X, Y, and Z. We're not going to take this and we're not just going to say in twistor space this is somehow CT plus I CT or something like that. We're not going to do X plus IX or something. That's just weird. We don't do that. What we're going to do to complexify things is to say our spacetime point here, or our spacetime distance, if you will, is this thing right here, and it's going to act on a 2-indexed thing. We don't really know exactly what this thing is yet, but it's going to act on this thing, and then it's going to give us a new 2-indexed thing. We're going to allow these things to be complex valued, okay? And when we allow those things to be complex valued, then what happens, or what's going to happen, is we're going to say, okay, Z alpha, this is going to be our twistor. It's going to be equal to Z1, Z2, Z3, and Z4. Okay, here's our Z3 and Z4, which is right here, and then our Z1 and Z2, which is right here. Okay, so this thing is our twistor, right? So the big thing here, this thing right here, is going to be our twistor. And the incidence relationship is this thing right here. So this is what we're calling the incidence relationship. This is the key to understanding what's going on here with Twistors theory. The idea here is that when we take a space-time point, we treat it as an operator, much like you would do in quantum field theory. You treat this thing as an operator. You operate on some 2-vector component thing. Again, these things are not the same thing. These things right here are not the same thing as this thing decomposed into vial spinors. Those are not vial spinors. These are two different things. We allow them to be complex, but when we allow them to become complex, we generalize this notion of spacetime into a more complex notion of spacetime, or what we would call complexified Minkowski spacetime. And visualizing this is actually quite difficult. Right? Because you can think about this as like, you have the space-time point and it's being treated as some operator. And that operator is acting on a 2-index component, kind of like a spinor. But this thing is also not quite, it's not quite a vial spinor. And it's being constructed into something, it's being constructed in a way in which this thing that's being operated on is going to be appended to this thing. So let's continue to see how this works out. So this is our incidence relationship. So this is a central relationship in twistor theory, where we say that omega alpha is equal to I, and you'll see this if you read up on twistor theory. You'll see this. This is this thing, right? So omega alpha is going to be this guy here, and pi beta is going to be this guy here. And so our twistor then is this guy, is this, right? So our twistor is made up of this guy and this guy right here. All right, so this is quite interesting. So we say that, okay, the spacetime point is acting on some two-component object, and that two-component object transforms into another two-component object via the spacetime point, and then we append those two things, and that thing is going to be a twistor. Okay? This is strange, but let's keep on going with this, and in later videos we'll see how this works as well. We're going to introduce a lot of quite advanced mathematical tools to really get into the weeds here, but let's just keep on going in this video. And so to understand this sort of geometrically, we can now take the determinant of this thing. So if we take the determinant of this spacetime point, we're thinking of this thing as our spacetime vector. And we kind of want to get into the gears here. We're thinking, okay, we are so used to thinking of space-time as a vector, as a four-dimensional thing, but now we want to take it as a 2x2 dimensional thing. And when we do that, when we take the determinant of that, we get this thing. And when we get this thing, then what is going to happen then is we're going to realize that a time-like separated events is when the time dominates, and so this thing is going to be greater than 0. Space-like separated events is when the spatial components, are dominate, and so this is going to be less than 0 because these are negative. And then the null separated events, and this is going to be key to twistor theory. Null separated events are going to be the case in which the determinant of this spacetime point is 0. And we can sort of make sense of this, right? So the determinant, so time-like separated events are events where your two events are just separated in time. They haven't moved in space, right? That's the easiest thing to sort of understand. Space-like separated events are generally not very understood well because we don't really encounter this sort of stuff in the real world. The idea here is that things are separated by space but not by time, so that would mean no time would have to pass in order for two, say, correlated events in space to have occurred, and so you lose this degree of causality. There's no link between the two events because if they were to happen at the same exact point, at the same exact time, that's instantaneous, and time and a light particle would not have enough time to pass between the two events because it's, again, no time has elapsed between the two. So space-like events are a little bit lesser understood, in my view, I think. Time-like events are the events that we always see in the real world. And the null separated events, this is going to be the events in which the time is chugging along just as much as the distance is chugging along, right? So the idea here is that light itself travels in the direction of x3 and the parameterization of the path that light is traveling is how we're going to parameterize time. So 1 second is correlated to 1 unit of distance that the light travels. So that is how we understand null separated events. Anyways, let's continue here. We're going to now take an example. An example is when all the spatial components, x3, x2, x1, those are all 0. And when those are all 0, we get this matrix, and we can do some manipulations here. We can use this matrix then use the incidence relationship, and when we get the incidence relationship, what happens is we get so we multiply our spacetime point, right? So we multiply our spacetime point up here like we did to Z3 and Z4, and then just multiplying by time for each one, and we get this. And then that should be negative, right? These guys should be negative, but I regain the negative right here, right? So these guys should be negative anyways. And so Z1, Z2 is going to be equal to negative IT Z3, Z4. So, and then so we get that, right? So if Z1 and Z2 is equal to this, well, our twistor was Z1, Z2, Z3, Z4. If this is equal to this, we just replace it down here. But we can also rewrite this. We can replace 3 with 1, 4 with 2, and we get this here. And so what we get is this right here. And this looks very, very reminiscent of these guys look very reminiscent of a canonical momentum operator. Right, so we have what looks like now to be a position operator, or positions of our twistor, and then momenta of our twistors. And this is a super important realization to make. In other words, the incidence relationship induces or makes it such that the upper two components of our twistor are analogs to position and twistor space, and the bottom two are analog to the respective momenta and twistor space. And we can do the same thing for if we were to set t equal to 0, so have just two space-like separated events in twistor space, and what ends up happening is we get something very similar down here. We get what looks to be like these operators acting on these positions, and so we have this four momenta going on, right, with the ddt and ddx, and then this thing here that needs to go away. That's not a thing. But anyways, the idea here is that 4D motion in spacetime is going to correlate, right? It's going to, not 4D motion in spacetime. The idea here is that these guys here are going to be analogs to position in twistor space, and these guys here are going to be analogs to momenta in twistor space. 4 momenta, right? So in general, now we can do this for in general. In general, a spacetime vector separated by both time and space now in our twistor space is going to look like this, right? So we don't make anything 0. We change t for x 0. That's what we do all the time in physics. And we just do this vector multiplication. And when we do the vector multiplication, we get this, and then multiplying things out, we then take our this guy here and this guy here, that's this right here. Okay, we're just, and again, because this is just matrix addition or subtraction, not matrix, vector addition or subtraction, and then we take this guy, then we go here, right? So from here to here, then we're just taking, you can do this multiplication, you can see that you get this. And so again, because this is a 2 by 2 vector, it looks like, not really because there's so much stuff in there, but that's a 2 by 2 vector. So that gets broken down into this, and then we get this right here. So in general, then we have our incidence relationship then is now this in general. So we have this mixing. This is a weird mixing, right? So the idea here is that 4D motion in space-time, or you move in time, you move in 3 dimensions in space, that correlates with a mixing of components in twistor space, right? Because we have this mixing going on right here, this mixing right here. So that's very strange. So twistor space, when you move in space-time, you twist, if you will, in twistor space, right? Because we have this twisting of the components. Okay, we're starting to hint at why this might be called twistor theory. There's a little bit more to the name than just that, but we can almost think that motion here in space-time correlates to twisting motion in twistor space. So with that, let's just from a bird's eye view then. Minkowski space, we went from Minkowski space to twistor space, and we used the incidence relationship. And what we found was that motion in space-time is going to be sort of twisting in twistor space. So with that, let's now look at this. What we want to do now is we want to look at the code of this. I've coded a little bit of an animation up. We saw that earlier. So let's go ahead and dive into that. Alright, so what is some science without a little bit of code? So we're going to go over that animation that I showed you guys earlier. And that animation is an animation of the incidence relationship. Okay, and what we're going to do is I'm going to take you through the code a little bit, and we are going to see what values we can change, what we can do to this code. If you're interested in this code, this will be posted on my Patreon if you want to play around with this, if you want to use it in your own projects and so forth. But let's look at the animation again really quick. This is really just, again, an animation of what happens when I'll play this really quick, when we modulate x0, x1, x2, and x3. And again, we have to take into consideration, and you can do this by yourself if you want, you have to take into consideration that x0 and x1 are going to have to move together, because that's what constitutes the Lorentz transformation. It's a transformation of space and time, or it's a transformation in space-time. So you can do those calculations to see what these values should be, and then you can modulate this accordingly. But the idea here is that when we play this, we're modulating the values of x0 and x1, right? So x0 is how temporally distanced two space-time points are from each other, and then x1 is how spatially distanced they are from each other. And we're using this equation that we talked about earlier. And so when we modulate these two values, we can see this arrow. This is sort of the twistor space. This is what's happening in twistor space as these values change. In other words, as we get really far in space here, and you can sort of change the rates by which these are going together. We can actually do that. I won't do that right now. It takes a little bit of time to render, but we can play around with these. So let's go ahead and do that. So here's the code. Again, I just have this in a file name. When I run this, it should get posted into the Twistor Theory, my Twistor Theory file here. Then there's a bunch of stuff I can change, right? I can change the figure width, the figure height, the amount of time it takes for this animation to run, and all this, right? So this can be all changed and everything. And we can change font colors. This is just for aesthetic purposes. The vector specific parameters, right? So again, the arrow color and the trace color. Notice when I go back here, this traced out this line to really sort of help us understand, to understand what path this is taken. But we don't want it to be too cluttered, so I have it fading out every, I think, 5 seconds, and it's tapered to give it somewhat more of an elegant look as well. And so, okay, so we have this. Let's go back. The visible trace duration. These are the parameters that are going to dictate how long that trace hangs out for. The real creme de la creme here, if you will, is going to be in here, right? So the oscillation frequency of x0, of x1, x2, and x3. These are going to be. This is going to tell us how fast these values over here are going to change, okay? And with a little bit, and then we could say we have these all start at 0. We can have them all start at the origin, if you will. And then these circles, right? So these circles are just, again, a little bit more for aesthetic purposes. These are these concentric circles. You can have them expand outwards even more if we want, but I just put them, a few of them in here. So that's setting up those circles. Plot limits, right? So the plot limit, that's just going to be go up to 3i, negative 3i, 3, and negative 3. And the one thing that we want to keep in mind, right, that was a little bit difficult for this animation was that when we look at the equation, what you notice is that Z1, Z2, Z3, and Z4, those are actually complex vectors, okay? So if what you're doing here, or what we're doing here, is we're just animating a part, really just a part of this, right? Because this is a single object. This is a single vector. What we have is a vector of vectors, right? So we can't really animate all of that. I mean, you could in some interesting and unique way, and I'm actually working on that at the moment. But right now we're just really looking at a part of this, because again, that in that equation we had a vector of vectors. Here we are just looking at a single vector. So this is not totally complete, just keep that in mind. But this is a way of taking a look at all of this, or not all of it, but some of it. And so this is where it starts, right? So I have my metadata, the title of it, I'm the artist here, and all this. And you can go ahead and you can take a look at how this is all structured, right? So we have Z3 in and Z4 in. Those are the two input vectors. Those are the two vectors that are getting inputted, and they're going to be transformed by our vial vector. And so, and then we have these guys here. These are the entries. And then we just scale everything. We calculate the first part of the transformation. So I'm doing this in parts. And eventually and then this is just plotting, this is more aesthetic stuff. You can go ahead and change any of this if you want as well. Another key thing here that I want to sort of get to you guys is that we can change colors if you want to change colors as well. And we have our axis coordinates, right? Our axis coordinates, and then we just label everything, right? So this was the tick labels for that right graph here, over here. Those are those labels. We have to normalize the normalized values, and this is all just aesthetic stuff here, just to make the animation look nice. But again, if you are interested in the code and you want to play around with it, you can hit up my Patreon page and get the code there. And the code has not been posted yet on the Patreon page because no one's really taken an interest in that tier yet, but once they do, code will start going up. So with that being said, that is going to be the end of this video, and I will see you guys in the next one. In the next video we're gonna start talking about how we can split octonions and or quaternions and all that fun stuff, because we need to understand conformal field theory as well, and we want to understand conformal transformations because those are going to be very important. So with that being said, I will see you guys in the next video. Bye.